All right, so today in probability and statistics, we're going to start chapter 5, which is on something called discrete random variables. So this is kind of an extension of what we did in units 2 and 3, where we did probability distributions and frequency distributions. And we're going to get into that a lot during this unit. It's kind of a smaller unit. It's only, I think, 4 lessons. And so let's go ahead and get started. First of all, we're going to begin by looking at an event that happened in 1989 that you may or may not be aware of. But what happened was there was a hole-in-one on the same hole in Rochester, New York at the Oak Hill Country Club, where 4 golfers each got a hole-in-one on the same day in the same tournament. This only happened in the 88 years leading up to this event. It only happened 14 times, and on this particular day, it happened 4 times on the same hole. And so different people wrote about it. You could read about it in different articles. One article said that the odds for this happening was 332,000 to 1. But another article said the odds were this. So let's see, that's going to be the ones. We have thousands, millions, billions, trillions. That's 1,890,000,000,000. I lost track. So this is the thousands, the millions, the billions, the trillions. So 1,890,000,000,000,000 to 1. So who's right? These are the type of odds that we're going to be talking about in this unit. So that by the time we are finished with this unit, we're going to come back and visit this problem and see if there is a way that we can figure this out. Maybe in the same way as one of these articles or in a different way, or maybe get something in between. And that's what we're going to work on during this unit. So we're going to start by doing lesson 5.1, which is on discrete random variables and probability distributions. So let's go ahead and get started. First of all, I want you to take a look at this table. This is information from one of my Algebra 2 classes, where I just asked kids how many siblings they had. And so you can see from the chart there were several people that were only children. 8 out of the 40 students were an only child. And then there were 17 of the students had 1 brother or sister, 11 had 2 brothers or sisters, 3 had 3 brothers or sisters, and I had 1 student that had 4 brothers and sisters. Okay, and so this is a discrete random variable. One of the things we're going to use is random variable notation, which looks like this here in red, and it's called a discrete random variable because if I ask another person, let's say I had 1 more person in my class, so I had 41 students, and I asked them, that would be a random variable. And it's discrete because their answer could be, it's not an infinite set of possibilities. It's just a finite set of possibilities. Now, it could be outside of 0 through 4. They could have 10 siblings. And so, but it is still a discrete. I can't have 3.5 siblings or something like that. It's a discrete random variable. And so we could describe this random variable as x. So x would be the number of siblings you have. And this notation would be the probability that the x is equal to 2. In other words, what is the probability that a randomly asked individual in my honors algebra 2 classes would have exactly 2 siblings? And the answer would be 0.275. And that's relative frequency or random variable notation. So what is a random variable? Random variable is a quantitative variable, which means it's a number whose value depends on chance. That's a random variable. So we've talked about that in the past. A discrete random variable is a random variable whose possible values can be listed. So if it's a random variable with only a finite number of possibilities, so if it has a finite number of possibilities, then it's called a discrete random variable. So examples of this would be the number of siblings you might have, the sum of 2 dice when you roll a pair of dice, the number of puppies in a litter, the lifetime of a flashlight battery. Now this would have a lot more, and if we would have to round this one like to the nearest minute or the nearest hour, okay? But it could be 10 hours, it could be 200 hours, or it could be 2,000 hours, depending on how good the battery is. But it wouldn't last forever. It would be finite. So then we're going to talk about the differences in two different things. We're going to display this two different ways. One way that we would display this information is with what is called a probability distribution. We've talked about this in the past. It's just simply a listing of all the possible values and their corresponding probabilities. And then we're going to put that on what's called a probability histogram, which is basically a graph of those probabilities. Let me just give you an example of what this is going to look like. So here on the left, we have an example of a probability distribution. So you could have your number of siblings here, 0, 1, 2, 3, and 4. And then here are the probabilities of those different siblings happening, at least with my Algebra 2 class. Okay, you can see that the total is 1. The total probability would add up to 1, okay, because there wasn't anybody outside of this group. Okay, it's going to be exhaustive. And then over here we have what's called a probability histogram. So if we take each of these probabilities, like for example, the probability that you don't have a sibling is 0.2 or 20%. So 20% of the people that were in my Honors Algebra 2 class were only children. That's 1 out of 5. 42.5% of them had one sibling. So that we listed that over here with this bar. This is a histogram, so the bars are touching each other. Okay. Probability that you had 2 siblings was 0.275, or 27.5 had 2 brothers or sisters. And then it started to go down. 7.5 had 3 siblings, and I just had 1 student. 0.025% of them had 4 siblings. So this would be a histogram. And so what we're trying to do with the histogram, and as we'll discover this as we go throughout this unit, is we're trying to get like what does the information look like if we spread it out. So this is kind of like a bell curve, maybe pulled a little bit to the right, but you can kind of see what the distribution looks like. We're going to get more into that as this unit goes on as well. All right. So here we wanted to notice that the sum of the probabilities is always equal to 1. If we go back here, you can see that the sum of the probabilities down here is always equal to 1, and that's what I want to just point out here. So what this means is the sum of all the probabilities of x, and this is all the individual x values, so it could be 0, 1, 2, 3, or 4, but that's going to equal 1. So let's take a look at an example here. So we have an elementary school, okay, with different grade levels, and each of these different students are in a grade level. Actually, this probably would not be an individual school, but maybe this is everybody in the city of Fort Wayne, Indiana. So we have in the city of Fort Wayne, Indiana, maybe this is kindergarten, 4,819 kindergartners. And in first grade, 3,708 first graders. Or maybe this is a school district. It would be bigger than what Homestead and what Southwest Allen County Schools is. Maybe this would be Fort Wayne Community Schools. But anyway, it says use random variable notation to represent the event that the selected student is in 5th grade. So here we're talking about this line here. We want to know what is the probability that they're in 5th grade. Well, the probability notation is going to look like this. Okay, so it would be the probability that y, which is your grade level, so the probability that your grade level is, there's your equal sign, is 5. So the probability would be 3,629 out of the total 34,169. And I believe that is 0.106. So that would be 10.6% of the population of kids from grades kindergarten through 8th grade. The probability is 10.6% that they are in 5th grade. So then if we want to determine the probability distribution, that would look something like this. So we would have all of these frequencies, okay, how many kids are in each grade level, we would turn them into probabilities like we have over here. And each probability would be the number in that grade level, like the number of kindergartners divided by the total amount. And so for kindergartners, there would be 14.1% of the kids are in kindergarten. And the one that we did earlier, fifth graders, there's our 0.106. But this is an example of the probability distribution. Let's take a look at another example. So in this example, suppose we flip 3 coins. We have 8 equally likely outcomes or possibilities. So you can see up here that one of the possibilities is that we get all heads. So we could have a heads, heads, and then a tails. So there's my second possibility. The third possibility, we have a heads and then a tails and a heads, or we could have a heads, tails, and tails. All 4 of these possibilities begin with a heads, but there's no other possible way to begin with the first one being a heads. So if we move on here, let's say it begins with the tails and then 2 heads. We could have a tails, a heads, and then a tails. Or tails, tails, and heads, and the final possibility would be tails, tails, tails. So if we let x denote the number of heads obtained in the 3 tosses, x is a discrete random variable and it has 4 possible values. It's either going to be 0, 1, 2, or 3. It's either going to show up 0 times, or we're going to have a heads once, or a heads twice, or a heads 3 times. So let's say we have some questions here that we want to answer. The first one would be use random variable notation to represent the event that exactly 2 heads are tossed. Well, we can answer that one with this one right here. Determine the probability that x, that means a head is obtained, equals twice. So we want to figure out the probability that if 3 coins are flipped, that a heads is drawn or is shown twice. And that would be this right here. If I wanted to find the probability that a head shows up twice, well, I'd have to go up here and figure out how many times does a head show up exactly twice. Well, there's this one, there's this one, and there's this one. So that's going to be 3 out of 8, which is 0.375. So if I want to find the probability distribution for x, well, then I'd have to do something like this, where I'm going to make a table of values here, and over here I'm going to have all the different possibilities. So there could be 0, it could be 1, it could be 2, or it could be 3. I'll do it with my finger, maybe that'll be a little bit easier. And so I want to know what is the probability. This is my x here, that's my event. And so these are the different values of x. And then I want to figure out what is the probability of each of these events for happening. So for example, the probability that I get no heads, well, that's going to happen 1 out of the 8 times, which is 0.125%. 12.5%, 0.125 is a decimal. What is the probability that a head shows up once? Well, that would be here. It shows up once. Here it shows up once, and here it shows up once. That's 3 out of 8, which is 0.375. The probability that it shows up twice, we already did that over here. That's also 0.375. And the probability that a head shows up all 3 times, well, that's 1 out of the 8 times, which is 0.125. Notice that these all should add up to exactly 1. So then, suppose I want to use random variable notation to represent the probability, the event that at most 2 heads show up. At most 2 heads show up. Well, that would be, it could be 0, it could be 1, or it could be 2. So the probability notation would look like this. The probability that x is less than or equal to 2. Okay, that would include all 3 of these, which means I'd have to add all these together, which is going to be 0.875. So this is going to be equal to 0.875, which means 87.5% of the time we would have at most 2 heads that would show up. All right, so In a large number of independent observations, eventually the actual histogram of, or the actual frequencies would get closer and closer to what the actual probabilities represent. Okay, so this concept is very simple, or is very similar to the frequentist interpretation of probabilities. For example, if we only did this and we flipped 3 coins and we only did it 8 times, we might get the actual frequencies that are far different than the probabilities. But the more we do this, the more it's going to actually end up looking like what the actual probabilities would look like. Here's an example of this. Let's first go over here to the histogram. We had 0.125% of the time a 0 would show up. 0.375%, not a 0, but heads would show up 0 times. 0.375 or 37.5% of the times a head would show up once. 37.5% of the time a heads would show up twice. And then 12.5% of the time a heads would show up all 3 times. So if we only did this 8 times, the actual distribution might look far different than this. But if we have a histogram of doing this, let's say 1,000 times, it's going to be pretty close. It may not be exactly right on, like you can tell right here, this is not exact. Those should be the same, and they're not the exact same thing. If we did this 10,000 times, this would be a lot closer. If we did it 100,000 times, it'd be even closer. And the more attempts that we did, the closer the actual findings would be to the actual probabilities, which is over here. And that's section 5.1. And that should set us up for our assignment in Math Excel, which will be due tomorrow. Good luck, and we will see you tomorrow.